Beautiful morning it is, so make sure you get yourself out into the fresh air sometime today. We move on to very exciting calculations finally on Einstein's photoelectric equation. Okay, so remember what we looked at yesterday, crucial points, okay, light travels in photons, okay, and the energy of a photon is equal to hf. Okay, so you have that, have to know that, okay. The crucial point then that makes life easy for us, what Einstein says that a photon gives all of its energy to one electron. So one photon, one electron, we can ignore everything else. Makes the maths very easy, okay? And then we use the principle of conservation of energy and call it Einstein's photoelectric equation. So the energy of the photon coming in gives all of its energy to one electron. The electron requires energy to get released from the surface of the metal, and we call it the work function. And so it uses that energy first, and then if there's any energy left over, it's in the form of the kinetic energy of the electron. That's it. That's Einstein's photoelectric equation written in words. So to write it out mathematically, energy of the photon is hf, work function phi, okay, and kinetic energy we just always write as a half mv squared. Okay, we're used to that. And that's the core equation. That's it. That's the core equation for the calculations we're going to do. This separately also important, right? Now, okay, so as always we have a core equation, and then we have little equations that work with it that we may need to use if we don't have information. So for example, if we don't have the frequency, we will probably be given the wavelength, and in fact usually we are given the wavelength. So if we're not given the frequency, we have our mini formula, okay, from the waves section. C is frequency times wavelength. Okay, so C being the speed of light in air, frequency being the frequency of the light, and lambda being the wavelength of the light. Okay, so as we'll see when we're doing calculations in a minute, very often you're given the wavelength, so you'll use this formula to get the frequency, because C is a constant that we have. So in effect, this equation, as well as these beautiful equations that we like, there are only two variables. C is a constant, so f and lambda. So if you have lambda, you have f, and you just use that formula. So remember that we've used that technique many times already. It's just using different formulas with the same technique. No new maths. Okay, still junior cert. Very good, junior cert, ordinary level maths. Okay, right. Work function. Remember we said, okay, if we look over here, okay, E is equal to hf. If the energy is the work function, which is the minimum energy to get the electrons to be emitted, so instead of E we put in that, F becomes the threshold frequency. So we have this formula, phi is equal to hf0. So again, if you don't have phi but you have the threshold frequency, again, one of these magic formula, okay, only three symbols. Well, h is a constant, this unbelievably small number, Planck's constant, okay. So if we have the work function, we have the threshold frequency and vice versa. Over here, sometimes we're just asked for kinetic energy, so you could just put in EK here, but I think we just leave it as half mv squared, or else it'll be half mv squared equals, as we'll see later. Okay, that's it. That's it. Okay, and we'll see with calculations. There's nothing more. If you understand this idea, Einstein's photoelectric equation of words, you're able to write this down. It's in your tables anyhow. It's in the forward tables booklet anyhow. Okay, and you have your frequency. You have this formula that we've used time and time again. And work function, we have this work function is hf0, and that's also your maths tables, as it turns out, but you'll know it anyhow, okay? And then it's a case of just basically using those and driving on, right? Now, we'll move on now, and we'll do some calculations, and we'll see how it goes. Thank you.